Hello guys and welcome to my channel. In this session, I want to talk about design definition process, and later in this video, I will also talk about system analysis process. Well, if you want to find out more about these two processes, then don't miss this training session, and as always, have a good one. The purpose of the design definition process is to provide sufficient detailed data and information about the system and its elements to enable the implementation consistent with architectural entities as defined in models and views of the system architecture. System architecture deals with high-level principles, concepts, and characteristics represented by general views or model excluding details. System design supplements the system architecture, providing information and data useful and necessary for implementation of the system elements. This information and data details the expected properties allocated to each system element and or to enable the transition toward their implementation. Design is the process of developing, expressing, documenting, and communicating the realization of the architecture of the system through a complete set of design characteristics described in a form suitable for implementation. Below figure is the IPO diagram for the design definition process. Design concerns every system element, for example, composed of implementation technologies such as mechanics, electronics, software, chemistry, human operations, and services, for which specific engineering processes are needed. The design definition process provides the detailed information and data that enable the implementation of a particular system element. This process provides feedback to the parent system architecture to consolidate or confirm the allocation and partitioning of architectural entities to system elements. As a result, the design definition process provides the description of the design characteristics and design enablers necessary for implementation. Design characteristics include dimensions, shapes, materials, and data processing structures. Design enablers include formal expressions or equations, drawing diagrams, tables of metrics with their values and margins, patterns, algorithms, and heuristics. The design definition process includes the following activities. Prepare for design definition. Plan for technology management. Identify the technologies needed to achieve the design objectives for the system and its system elements. The technology management includes obsolescence management. Determine which technologies and system elements have a risk of becoming obsolete. Plan for their potential replacement, including identification of potential evolving technologies. Identify the applicable types of design characteristics for each system element, considering the technologies that will be applied. Periodically assess the design characteristics and adjust as the system architecture evolves. Define and document the design definition strategy, including the need for and requirements of any enabling systems, products, or services. Establish design characteristics and design enablers related to each system element. Perform requirements allocation to system elements for all requirements and system elements not fully addressed in the architecture definition process. Usually, every system requirement is transformed into architectural entities and architectural characteristics. Those entities or characteristics are then allocated to system elements, either by direct assignment or by some kind of partitioning. However, there will be some cases where it is impractical or impossible to transform a requirement into an architectural entity. In either case, it is important to do some degree of analysis or study to determine how best to flow down each requirement. It is good practice to try to do as much of the allocation as possible in the architecture definition process. Define the design characteristics relating to the architectural characteristics for the architectural entities and ensure that the design characteristics are feasible. Use design enablers such as models, for example, physical and analytical, design heuristics, etc. If the design characteristics are determined infeasible, then assess other design alternatives or perform trades of other system definition elements. Perform interface definition to define the interfaces that were not defined by the architecture definition process or that need to be refined as the design details evolve. This includes both internal interfaces between the system elements and the external interfaces with other systems. Capture the design characteristics of each system element. The resulting artifacts will be dependent on the design methods and techniques used. Provide rationale about selection of major implementation options and enablers. Assess alternatives for obtaining system elements. Identify existing implemented elements. This includes cuts, reused, or other non-developed system elements. Alternatives for new system elements to be developed may be studied. Assess options for the system element, including the cuts system elements, the reused system elements, and the new system elements to be developed using selection criteria that is derived from the design characteristics. Select the most appropriate alternatives. If the decision is made to develop the system element, rest of the design definition process and the implementation process are used. If the decision is to buy or reuse a system element, the acquisition process may be used to obtain the system element. Manage the design. Capture and maintain the rationale for all selections among alternatives and decisions for the design architecture characteristics, design enablers, and sources of system elements. Manage the maintenance and evolution of the design, including the alignment with the architecture. Assess and control evolution of the design characteristics. Establish and maintain bidirectional traceability between the architecture entities, including views, models, and viewpoints, to the stakeholder requirements and concerns, system requirements and constraints, system analysis, traits, and rationale, verification criteria and results, and design elements. The traceability between the design characteristics and the architectural entities also helps ensure architectural compliance. Provide baseline information for configuration management. Maintain the design baseline and the design definition strategy. Discipline engineers or designers perform the design definition of each concerned system element. They provide strong support or knowledge and competencies to system engineers or architects in the evaluation and selection of candidate system architectures and system elements. Inversely, systems engineers or architects must provide feedback to discipline engineers or designers to improve knowledge and know-how. The architecture definition process focuses on the understanding and resolution of the stakeholder concerns. It develops insights into the relation between these concerns, the solution requirements, and the emergent properties and behaviors of the system. Architecture focuses on suitability, viability, and adaptability over the life cycle, and effective architecture is as design agnostic as possible to allow for maximum flexibility in the design trade space. It focuses more on the what than the how. The design definition process, on the other hand, is driven by specified requirements, the architecture, and more detailed analysis of performance and feasibility. Design definition addresses the implementation technologies and their assimilation. Design provides the how or implement to level of the definition. The purpose of system design is to make the link between the architecture of the SOI and the implementation of technological system elements that compose it. So, System design is understood as the complete set of detailed models, properties, or characteristics of each system element described into a form suitable for implementation. Every technological domain or discipline owns its peculiar laws, rules, theories, and enablers concerning transformational, structural, behavioral, and temporal properties of its composing parts of materials, energy, or information. These specific parts and or their compositions are described with typical design characteristics and enablers. These allow achieving the implementation of the system element of interest through various transformations, linkages, and exchanges required by design characteristics, for example, operability level, reliability rate, speed, safeguard level, that have been assigned during the architecture definition process. Examples of generic design characteristics in mechanics of solids include shape, geometrical pattern, dimension, volume, surface, curves, resistance to forces, distribution of forces, weight, velocity of motion, temporal persistence. Examples of generic design characteristics in software include distribution of processing, data structures, data persistence, procedural abstraction, data abstraction, control abstraction, encapsulation, creational patterns, for example, builder, factory, prototype, singleton, and structural patterns, for example, adapter, bridge, composite, decorator, and proxy. Because it is sometimes difficult to define applicable requirements to a system element from the engineering data of the parent system, for example, in particular from the expected architectural characteristics, it is possible to use the design descriptor technique as a complement. A design descriptor is a set of generic design characteristics and of their possible values. If similar but not exact system elements exist, it is possible to analyze these in order to identify their basic characteristics. Variations of the possible values of each characteristics determine potential candidate system elements. It is important to understand that design definition starts with the system as a whole consisting of system elements and ends with the definition that is designed for each of these system elements, not just one of them, and how they are designed to work together as a complete system. System elements are identified in the architecture, although the architecture might only identify those elements that are architecturally significant. During the design definition process, it might be necessary to identify additional system elements to make the whole system work. This might entail embedding some enabling elements or services inside the system boundary. There is usually a trade-off between having an enabling item inside or outside the system. The architecture definition process could make this decision, but it might be better to allow design definition to handle this, since it is often dependent on other design trade-offs and on design decisions that are made along the way. Some of these additional system elements might be necessary to account for missing functions that were not identified in the architecture. For example, it might be determined that the various system elements should not all produce their own power backup, but instead there should be a separate system element that perform this function for all the other elements. This would be the result of a design analysis to determine the best place to put this function, or it could be the result of applying a design pattern to this particular problem. It might be necessary to provide feedback to the architecture definition process regarding these design decisions and trade-offs to ensure there are no negative impacts on the architecture as a whole. The architecture might or might not be updated to reflect these design details, since this depends on whether it is important to capture these features as architecturally significant or not. It is this holistic approach to design of a system that distinguishes these from design of an individual product or service. Holistic design is an approach to design that considers the system being designed as an interconnected whole, which is also part of something larger. Holistic concepts can be applied to the system as a whole along with the system in its context. For example, the enterprise or mission in which the system participates, as well as the design of mechanical devices, the layout of spaces, and so forth. This approach to design often incorporates concerns about the environment, with holistic designers considering how their design will impact the environment and attempting to reduce environmental impact in their designs. Holistic design is about more than merely trying to meet the system requirements. In this part, I want to talk about system analysis process and elaborate its details. The purpose of the system analysis process is to provide a rigorous basis of data and information for technical understanding to aid decision making across the lifecycle. This process performs quantitative assessments and estimations that are based on analyses such as cost analysis, affordability analysis, technical risk analysis, feasibility analysis, effectiveness analysis, and other critical quality characteristics. Those analyses use mainly quantitative modeling techniques, analytical models, and associated simulations, which are applied at varying levels of rigor and complexity depending on the level of fidelity needed. In some cases, it may be necessary to employ a variety of analytic functions or experimentation to obtain the necessary insight. The results serves as inputs into various technical decisions, providing confidence in the adequacy and integrity of the system definition toward achieving the appropriate system balance. This process is used by examples but not limited to mission and business analysis process to analyze and estimate candidate OPSCON and or candidate business models related to a potential SOI in terms of feasibility, costs, risk, and effectiveness. The stakeholder requirements definition process and system requirements definition process to analyze issues relating to conflicts among the set of requirements and particular those related to feasibility, costs, technical risk, and effectiveness, mainly performances, operational conditions, and constraints. Architectural definition process and design definition process to analyze and estimate architectural and design characteristics of candidate architectures and or system elements, providing arguments in order to be able to select the most efficient ones in terms of costs, technical risks, effectiveness, for example, performances, dependability, human factors, and other stakeholders' concerns such as critical quality characteristics, affordability, maintenance, etc. Integration process, verification process, and validation process to estimate the related strategies. Project assessment and control process to obtain estimates of the performance against established targets and thresholds, especially with respect to the technical measures such as MOEs, MOSs, MOPs, and TPMs. The result of analyses and estimations as data, information, and arguments are provided to the decision management process for selecting the most efficient alternative or candidate. In some cases, the results may be provided to the project assessment and control process if the information is needed to monitor the progress of the system against its system objectives, performance thresholds, or growth targets, such as the projected or modeled reliability early in the development of the system as compared to its reliability growth curve. Below figure is the IPO diagram for the system analysis process. The system analysis process includes the following activities. Prepare for system analysis. Define the scope, types, objectives, and level of accuracy of required analysis and their level of importance to the system stakeholders. Define or select evaluation criteria, for example, operational conditions, environmental conditions, performance, dependability, costs types, risks types. The criteria mainly come from stakeholder needs, non-functional requirements, and design characteristics. The criteria must be consistent with the decision management strategy. Determine the candidate elements to be analyzed, the methods and procedures to be used, and the needed justification items. Determine the need and requirements for an obtain or acquire access to the enabling systems, products, or services necessary to perform analysis of the SOI. Schedule the analysis according to the availability of models, engineering data, for example, OPSCOM business models, stakeholder requirements, system requirements, design characteristics, verification actions, and validation actions, skilled personnel, and procedures. Document the corresponding system analysis strategy. Perform system analysis. Collect the data and inputs needed for the analysis, highlighting any assumptions. Inputs can include models. Those models may be physical models specific to each discipline, allowing to simulate physical phenomena. Representation models mainly used to simulate the behavior of a system or system element. Analytical models or deterministics and stochastics used to establish values of estimates to approach the real operation of a system or system element. Carry out analysis as scheduled using defined methods and procedures for cost, risk, effectiveness, and validation of assumptions. Conduct in-process peer reviews with appropriate subject matter experts or SMEs to assess the validity, quality, and consistency of the evolving system with the stakeholder objectives and with previous analyses. Record and report in-process results. Manage system analysis. Baseline the analysis results or reports using the configuration management process. Maintain an engineering history of the system evolution from stakeholder needs definition to ultimate system retirement so that the project team can conduct bidirectional searches at any time during or after the system lifecycle. The methods are chosen based on time, cost, accuracy, technical drivers, and criticality of analysis. Due to cost and schedule, most systems only perform system analysis for critical characteristics. Models can never simulate all the behavior of a system. They operate only in one limited field with a restricted number of variables. When a model is used, it is always necessary to make sure that the parameters and data inputs are part of the operation field. If not, irregular outputs are likely. Models evolve during the project by modification of parameters, by entering new data, and by the use of new tools. It is recommended to concurrently use several types of models in order to compare the results and or to take into account another characteristic or property of the system. Results of a simulation shall always be given in their modeling context, tool used, selected assumptions, parameters and data introduced, and variance of the outputs. During a system's lifecycle, assessments should be performed when technical choices have to be made or justified, and not just to compare different solutions. System analysis provides a rigorous approach to technical decision making. It is used to perform evaluations, including a set of analyses such as cost analysis, technical risk analysis, effectiveness analysis, and analysis of other properties. A cost analysis considers the full life cycle cost or LCC. The cost baseline can be adapted according to the project and the system. The full lifecycle cost may include labor and non-labor cost items. It may include development, manufacturing, service realization, sales, customer utilization, supply chain, maintenance, and disposal costs. Technical risks should not be confused with project risks, even if the method to manage them is the same. Technical risks address the system itself, not the project for its development. Of course, technical risks may interact with project risks. The system analysis process is often needed to perform the technical assessments that provide quantification and understanding of the probability or impact of the potential risk or opportunity. System effectiveness analysis is a term for a broad category of analyses that evaluate the degree or extent to which a system meets one or more criteria. The effectiveness of the system in meeting the criteria in its intended operational environment. The objectives and criteria may be derived from one or more desired system characteristics, such as MOEs, TPMs, or other attributes of the system, and influence the details of the analysis conducted. The analysis is more than simply determining if the criteria are met, but also the degree to which they are met, or fall short or exceed. As this information is used to support trade offs and evaluation of alternatives, such as which candidates to develop further, where improvements are needed or cost savings are possible. One of the challenges of effectiveness analysis is to prioritize and select the right set of effectiveness objectives and criteria. For example, if the product is made for a single use, the maintainability and capability of evolution will not be relevant criteria. Various types of models and modeling techniques can be used in the context of system analysis. These include, but are not limited to, physical models, structural models, behavioral models, functional models, temporal models, mass models, cost models, probabilistic models, parametric models, layout models, network models, visualizations, simulations, mathematical models, and prototypes.